So Module A will cover chapters 9 and 10. The syllabus did have 8 and 9 together, but 9 and 10 fit better. 9 is a pretty brief chapter, and to me the material in 9 and 10 are basically interlinked and could have been put in one big chapter. But the topic is traverse and traverse computations. Now, in the book, section 9.1, the introduction, says it pretty well. A traverse is a series of consecutive lines whose ends have been marked in the field and whose lengths and directions have been determined from observations. So in traditional surveying by ground methods, traversing is the act of marking, actually measuring these angles and distances, and that will be the topic of our next lab. The previous modules we've talked about angles and azimuths and bearings, and it's all coming together basically one step at a time. So we look at figure 9.1 as an example of a closed traverse. In this example here, the instrument would be set up at A, and typically you would be backsiding E in this case and turning an angle right to B. Now through the course of this, you may make an angular observation onto a station somewhere for an azimuth mark. So for example, if this was geodetic surveying, there may be a published azimuth between A and azimuth mark. Or that may be a long sight where more commonly it might be a pair of GPS observed points so that a state plane bearing can be calculated from A to the azimuth mark. It could also be a reference mark set for a solar observation, which is, as we've said before, very rarely done. But using this azimuth mark, the angle right can be measured from A backsiding azimuth mark to E, and then you have a starting azimuth for your shape. Then you would observe the angle and distance out here to B, and then next you would set up on B, backside A, turn the angle, measure the distance to C, and so forth until all 1, 2, 3, 4, 5 angles have been turned and the lengths of all 5 sides of that shape have been measured. So total stations will measure a horizontal distance. Typically we still measure a slope distance and a zenith angle and convert it to a horizontal distance. Not all traverses get to be closed. Figure 9.2 is an example of an open traverse where started at A, went to B, went to C, and this is actually like a route survey where deflection angles are measured. Now again, if you think about the previous modules, all of the azimuths can be computed for each of these lines using the deflection angles and the beginning bearing here of north 16 degrees 35 minutes east from A to B. And notice that north is not right up the page. It is more angled over here like this. Imagine taking the north there and moving it over. So, and here the distances are not actually spelled out. It's converted to stations. So like from D to E, you'll need to subtract from 1661.7, 1205.0, and you come up with something like 456.7 for the distance from D to E. Now here, figure 9.4, the book talks about in section 9.4 and 9.5 selection of traverse stations and referencing traverse stations. 2 different topics, but it all goes together with what you do on the ground. So if you're needing to perform a survey and you have to set up a traverse, the first thing you do is you go recon what you need to locate. To include, we tie flagging up over it. This may include taking a machete or a bush axe and trimming understory leaves and branches out of the way so that you can see where everything is. You might do this, might be covered in future courses if it's a boundary survey, which it most likely would be, to reconnaissance and find some property corners, fences, features that need to be located, etc. Once you know where you're going to go, then you go set up the traverse. And you're looking for a clear line of sight. It's ideal to be near the property line, but it's not necessary. Especially if the property line is particularly thick, overgrown, or has a lot of fences around it, you might not even be able to set up on the actual property line if you wanted to. So you have to select places where the ground is typically nice and level, pretty firm. You're probably not in direct sunlight. You even have to think about things like, are the bee nest or ant beds nearby? Are you within reach of a chained dog that really wants to eat you alive? These things all come into play in the field. It's usually beneficial to have your traverse stations set so that you can find them when you come back. If you have to come back, like you might have to come back to set a new pin, look for other pins. And when I say pins, I mean an iron pin that would mark a property corner. So in referencing a traverse point, you might observe some things that have nothing to do with the survey, like in figure 9.4, a fire hydrant and a couple of trees, all at pretty good angles. Why would you do this? Let's say that your traverse point is right here in this grassy area between Wolf Road and Brookfield Avenue, and you need to go back 2 months from now and find this point. They've cut the grass every week since, and there is no clear indication of it. You put a flag stake or a wooden stake next to it, and it's long gone. You can't even find it. Somebody didn't like it and pulled it up. But what you could do is measure 14.32, which is really silly to measure to the 100th to a tree. 28.45, a little bit more, but not a whole lot more practical, is measuring to a fire hydrant to the 100th of a foot. But you could take a pocket tape or a reel up tape and measure from the fire hydrant and the maple tree and the oak. Probably just 2 of these would be enough to get you in the right spot, and then with a metal detector you could find it. Now, part of the reason that this is still in textbooks is it's very common practice in the southeast that traversing is done using magnetic nails. For example, I use 6-inch long magnetized nails with a nice divot and a square on the top of it for rods to set in, for instruments to be able to be set up precisely over, and they are easily found with a metal detector. In some areas, they still use hub and tacks, or just hubs in some cases, so I'm told. And a hub and a tack is a wooden peg that's usually driven down into the ground flush, and then a stake tack, which is only about 1 inch long, very sharp, is mashed down into this stake to make a precise point to set the instrument up over. And those are nearly impossible to find with a metal detector because they only have a very small amount of metal, and some of them may even be aluminum or a type of metal that wouldn't carry a charge very well. So referencing it is just something that you would put in the notes, or you might just turn the angles and distances to the fire hydrant and the 2 trees so that you would know where they are. Power poles, street signs, storm drainage structures, these are all good reference points. So figure 9.6, talking about field notes for traversing. And as I've said before, field notes are like opinions. Everybody's got one, but if it works, everybody's got one. A lot of them are very different. As long as it works, then it's okay. Now let's look at this format here. One of the things that I say is it needs to be able to be duplicated and understood by others. And so even though they have made their letters and numbers correctly, obviously it's electronically prepared, they've got some information in here which this works, but I would I would just say this is not the most proficient note format in my experience, and I'll provide a better note format with the lab instructions for the Traverse. But it's all the same, regardless of how it's written out or explained. Here, the instrument is at station 101. Height of instrument is 5.3. Height of the rod is also 5.3. I find that kind of hard to believe, but moving ahead, station sighted 104. And the first angle is 0. So they're not coming out and telling you, but they're referencing this. The station or the instrument is at 101 and your back sighting 104. And your forward point is 102. And here again, typically we'll use point numbers so that they make sense. Commonly I would use a low point range for the initial, for my control points, like say 1 through 20 or 1 through 19, and start my Traverse at 20, or my side shots at 20. So that, I typically would say instrument at 2, that's the first place I set up, and back sight 1, which is the first place that I back sight, and then my next point ahead is 3. Then I move up and occupy 3, back sight 2, foresight 4, etc. And it tends to make sense. And you can kind of see over here, he's got a sketch on the right side. This is the sort of sketch that we're looking at, just to give us some relevance. This is not to scale, this is not detail, this is just something that you would do in the field book while in the field for relevance. So here what they're saying is they've set up on 101 first, down here at the bottom. They've back sighted 104, there's their 0 angle, and they've turned an 82-degree angle to number 102. Then they set up on 102, they took a sight of 0 on 101 and then turned a 95-degree angle right to 103. And then they moved up on 103 and turned in on 104. Now this is only 3 of the 4 angles, but also let's look at 82, 18, 19 is the direct angle to 104. And here is a zenith angle and horizontal distance. This really should be slope distance so that you don't get them confused. We're measuring basically three-dimensionally in triangles. The distance is measured from the instrument to the rod, which is the slope distance. We also know the horizontal distance and the vertical difference, or the elevation difference. So if you want to record the elevation difference, then I guess that makes sense to include the horizontal. You could compute the slope distance from that. And if you're not keeping track of elevations, it's not a bad idea just to take the horizontal distance. We'll cover that more and see it in a lab. Then they're doing a direct and reverse. Again, we're not going into multiple observation in this class or in this lab, but this is how you would do it basically. Is you'll notice that 180, the inverse should be at 180 degrees difference. From 0 it should be 180 degrees difference, or 180. And here they're saying that it's 3 seconds off on the back side, and they've got, it looks like 1 second difference because it's 18 is 1 second difference to 19, but you really have to look at the angle turned from 3 seconds over and realize that you're actually 4 seconds under, because that 3 seconds adds to it. You get a computed angle. Now for simplicity, we're just going to turn single angles and process those, but this is one method of multiple observations on a point, which is to back sight with 0, turn your forward angle, then you reverse with 180, and you turn your angle right in the reverse mode. And here you'll see your zenith angles are inverted. So again, there's a lot of different formats, but that's what we're doing, is we're collecting the interior angle. Typically might be the exterior angle of this shape. So let's talk about that. This is interior angles, but what if we set on 101, back-sided 102, and turned an angle to 104? Then we're going to be turning this angle, which is an exterior angle. We also need to talk about at this point that we have to understand the sum of the interior angles is the number of sides minus 2 times 180. That becomes pretty important as we go forward. For example, in a triangle, you could have equal-sided triangle, and you're going to have 60 degrees at each corner of the triangle. There's 3 sides. 3 minus 2 is 1. 1 times 180 is 180, and that adds up. A 4-sided figure could be a square. You got 4 right angles. That's 90 degrees times 4 is 360. All right, 4 minus 2 is 2. 2 times 180 is 360. So we know exactly how many angles or how many bearings, how many degrees, minutes, and seconds there are on the interior of any form. Even if there's 1,085 sides to a huge traverse, it would be 1,083 times 180 would be the sum of the interior angles. And that's how we compute for angular error. Now, before we get into that, figure 9.7 uses a term that I don't really like. It says radial traversing. An example A here on the left, from one occupied station. Figure B on the right is from 2. So you got like, basically they're saying you set on O, you take a backside on Z, and you turn an angular distance to A, then to B, then to C, D, etc. And you can compute coordinates on A, B, C, D, E, and F from O with a backside on something to establish a direction. Figure B is a little confusing, but let's just say that you set up on O prime and turn angles and distances to these same points. You could get competing sets of coordinates and average them. That's just not a standard approach that I've ever heard of or encountered on an exam. But figure A here is something that we might do. Basically, at any point, let's just say that O is just a traverse point along the way, and we're locating a property corner. Getting 2 shots on the neighbor's fence so that we can show where it is. F is a well where they draw water. E is a building corner. Let's just say that instead of that, let's say that D and E are corners of a large metal building. So we want to locate the 2 front corners of the metal building. This could be something that's very commonly done when you're sitting on this traverse station O right here. You're going to have things to locate, and then you might move on out over here to the net. Maybe you're going to go move up on Z in figure B. But radial traversing is I think a bad choice of terms. This is just what we call radial side shots. And side shots are just points that we shoot off to the side. In levels, we call them intermediate foresights or intermediate points. That's all we're saying is that these are points that we located. We had reason to need the data for them as we went by. Figure 10.1. We're moving into chapter 10. Just this quick because, as you see, the topics really interlink. What we got to do with our traverse is not just go out and measure it and say, yay. That doesn't really accomplish anything. If you remember in the differential and the trigonometric level loops, our purpose was to obtain balanced or adjusted elevations for those points. We were looking for one of the 3 coordinate values, the Z or elevation value for our turning points. In a traverse, we're looking for finished coordinates. We're looking for bearings and distances between them. We will also be looking eventually at area between some of these points, and just assume there's something should be taught in survey 2 about state plane coordinates and projections, where you might get state plane grid coordinates. But for this purpose and in simple traversing, we will just assume a northing and an easting, which is y and x. Now keep in mind, in your coordinate geometry and background and anything you've done in trig so far, coordinates are always in X and Y. In surveying, it's always been reverse. And this goes back to medieval times and circumnavigating the globe and things. The north value is always just the one that they used first. I'm not sure who came up with, in modern mathematics, the idea to come up to use the X value first. But in navigating and surveying, the north value always came first. So coordinate pairs in the land surveying world are always given as north and east. So we go out, we stick a control station in the ground, or we set up on somebody's control station, or like in our labs, we've got the capped rebars. It's A. I like numbers, the book likes letters. And they're going back here and they're saying, you know, W is this remote point that we're getting our bearing from. In reality, we're either going to be having some known bearings that we can rotate to later, or we're going to be taking a compass bearing from our first site or our second site. But you know, in this example, you know, we're setting up on A. We're saying that we are at elevations 5,000, 10,000. I guess one advantage to that is, you know, the 5,000 range is going to be your northing, and your 10,000 range is going to be easting. Let's say you're going to start at A. I guess your first backside would be E, and then you would turn an angle right, which is signified there, and measure your distance using the known bearing for W. Then we can compute the starting bearing of our traverse from B to C by adding, you know, we might just have this angle from our W, our azimuth point, to E, and then add that to, you know, to the angle right turned from A backsiding E to B. And I hope that you can follow this. This is all we're doing, is we're measuring these angles and distances. We'll record them in the book like we'll discuss further, but just understand we're collecting data, even if, you know, in the real world, most likely be with a tablet or a data collector. As I said, the angles, the interior angles measured here in the previous diagram at A is 100 degrees, 45 minutes, 37 seconds. I'll not repeat all them, but they come out to 540 degrees, 0 minutes, 11 seconds. There are 5 sides to this shape, so 5 minus 2 is 3, times 180 is 540. So the correct sum of the interior angle rights should have been 540 degrees flat. We have 11 seconds of traverse error. Now there are basically 2 methods for old longhand correction. I don't care which one you use, and I don't really want to complicate the matter. But in this case, you've got 11 seconds of angular error divided by 5 angles turned. That's 2.2 seconds per point. If you're reporting angular error, there you go, 2.2 seconds per angle point. Or you can just round it to the nearest second or whatever unit you're measuring in. So yeah, you would round that to 2, and eventually your 6.6 becomes 7. But you're adding this to each, to the sum of the angles, which you would be adding the sum to the azimuths, but to the interior angles, you're just adding this to each. So this interior angle, if you add all these up by 2, 4, or by 2, 4, 7, 9, and 11, the adjusted angle comes out to, you know, this, it differs a little bit. This one changes by 2 seconds. The next one by 2 seconds, 43 to 41. The next one by 3 seconds, which is where your 2.2 times 3 comes up to be 6.6 and rounds. So, you know, if you're using a calculator, you don't have to worry about which method you're using, but they'll change it by the interior angle will change by 3 seconds at this point. So once your adjusted angles, where you've added the proportionate amount of angular error into each setup, you come out at 540 exactly. This other method, you would add 2, then you'd add 3, then you'd add 3, then you add 1, then you add 2. That comes up to 11. Your adjusted angles are similar but a little bit different. We're talking about 1 second, which is microscopic differences, but this also causes it to sum. Now this method 2 is taking traverse legs into account just a little bit. So they're putting more angular error into the longer sights, which in theory you should have less angular error in the longer sights because you have better focus. Now we move into section 10.3 in the book, computation of preliminary azimuths or bearings. Now we're always going to use azimuths because that's just how math works really good. We already covered basically how to do this in the previous module. Let's just say that we're trying to find the azimuth from B to C. That's what the title of figure 10.2 is. So we're sitting on B and we're backsighting A, which has B to A is a 306, 55, 17 back azimuth. B, the angle turn is 231, 23, 41. So your azimuth is 306, 55, 17. Convert that to decimal hours. Add that to your angle, 231, 23, 41. That's your angle observed. That comes out to 538 degrees. So we know right there we just want to stop and take 360 off, because once you rotate past the north arrow, you take 360 off. And you come up with 178 degrees, 18 minutes, 58 seconds. That is the azimuth from B to C. It is no more complicated than that. That's all. Where this does come into account is when we adjust and minutely bump that error out until it basically goes away or is equally compensated for, is our angle turned at B, it might turn out to be 44 seconds instead of 41. So this might change our azimuth out. So we typically want to, we would love to just look at our figure, compute our raw angles, compute our angular error, then adjust our interior angles, and compute our azimuths only once. Software makes it really easy to compute a raw angular error. Well, we'll always do that, but error of closure, where we're able to figure out what the horizontal error is, which we're about to get into if we did not adjust our angles. But what we want to do is adjust our angles first and then use our adjusted angles to compute our azimuths for our traverse computation. Now, you go to section 10.4 in the book, latitudes and departures. That's all we're doing here is delta x, delta y, delta north, delta east. The departure is the term for departure x, departure east. Latitude is the departure north or the departure y. We could use the terms difference east, difference north, but the term that's been around longer than any of us is latitude and departure. Now the book says departure and latitude. I've always heard it called latitude and departures. Very simply put, you've got the azimuth of the line from A to B. You've got the length of the line. You've got everything that you need to compute it. Say you know the coordinates of A, say it's 5,000, 10,000, you compute the latitude, add that to the northing, that's the north coordinate for B. You've got the coordinate for E, you compute the departure, the east coordinate for A, you add the departure, the difference east to it, and you get the east coordinate for B, and then you've got coordinates on the new set. But the latitude and departure are the parts. Now this is a little bit more detailed. I'll provide this in the module. So this came from Professor Branham's course material for section 10.4. So after balancing the angles, calculating preliminary azimuths, and the traverse closure is checked by computing the latitude and departure of each line. Computing these allows you to determine the linear error based on the distances measured for each line. Like angular error, when measuring the distances of the traverse, we must find out and balance out the distance or linear errors. The latitude is its orthographic projection in the north-south y-axis. That's being a little wordy. And is equal to the course length, or the leg, the horizontal distance from A to B, multiplied times the cosine of the azimuth. Latitudes are more commonly known as change in northings. As we were saying, the departure is the azimuth times the sine of, or the sine of the azimuth times the length of the course. So, here's just a good example. Don't round it too far. He's got, final answer rounded to the nearest 4 decimal places, and typically we'll carry coordinates to 3 or 4 decimal places, not 2, in our computations. Now, we may report to a lower order, but we want to carry them to 4 decimal places. We'll carry them to 4 decimal places in this class so that people will not lose rounding error. Remember to always convert your angles to decimal degrees. Don't trip up and use your minutes and seconds. There's a lot of conversion back and forth, but it's really not that hard. You just have to take your time and make sure that you understand it. So here, this is a great example. A, whatever the coordinate is, we're not really worried about the coordinate, but we're looking at latitudes and departures. The latitude, we take the azimuth is 126 because it's south 5304 east. Let's just say that we computed that from our traverse computation, and angles turned. A to B has an azimuth of 126, 5517. You take the cosine of that, of 126, multiply it times 647.25, and you get 388.8152 for your latitude. That's your difference in north. It's negative, so you're going south. And that makes sense. You're actually going south over here. The departure, you take the sine of the azimuth times 647.25, and your departure is a positive 517.458. So you've came out to the east 517.458. You've come south 388.8152. So if you have a coordinate of A, the coordinate values, you subtract the latitude, add the departure to the easting, and that gives you coordinates on B. Whether that's computed or actually it's going to be raw in the case of how we prepare traditional traversing notes. And here's how it is. Station A, you got this azimuth, 126.5517, length of 647.25. Here's the latitude and departure that we just talked about. You take that for each of these 5 sides. Now you know the length. The departure should sum to 0, just like our differential leveling loops. And so should the latitude. And it looks like my face takes out part of it, but here's table 10.3. That's 0.077 is the sum of the latitudes. So this traverse has an error of 0.026 in departure and 0.077 in latitude. So your north error 0.077, your east error is 0.026. You can just use the good old Pythagorean theorem. Say 0.077 squared plus 0.026 squared. Square root of that is 0.813. The linear error of closure is something that we're always interested in. It's not that complicated. It's just the distance traversed divided by the error. And so in this case, 2466 divided by 2466 divided by 0.0813 is 1 in 30,342.87. So in theory, at that level of precision, in 2,466 feet, we picked up 800ths of air. In order to get a full foot of air, we would have to traverse at this same precision rate, 30,342 feet. So that's very precise, adequate for most boundary surveying elements. Now, let's get a little bit more tricky. Table 10.5 showing us how to balance traverse azimuths. Again, this is if you go about it with your unadjusted azimuth, then you put your angular error in, which would accumulate if you got 2 seconds per angle point. In this example, you do. So you wind up adding 2, 4, 6, 8, 10, and that takes your unadjusted azimuths and corrects them so that they reflect your adjusted interior angles. Traverse adjustment by coordinates, this is what we really want to do. Is, they're saying preliminary azimuth here in this table. It's really just your azimuth. We're not really, we're not really coming in and determining a preliminary azimuth and then coming back and computing a final azimuth. We're going to go ahead and balance the angles as we go. This is common practice. And we're going to create we're going to compute our adjusted angles, or our adjusted azimuths for our angle start and the sum of the angles, or the adjustment. So these would be the adjusted azimuths here. Again, going right back to, we got the length, got the azimuth, compute the latitude, the departure. A is at these coordinates, and then you just add your latitudes and departures. They come around. They call it misclosure, which is another term for error. I like the word error. The book uses them both. The error in X or in east, and see they've got this reversed from how surveyors typically do it. They've got X and then Y. But your error in X or in easting is 17 or 1800ths, 0.179 feet, and the difference north is 200ths or 0.024. Now, what you do here is, of course, this computes, this is doing the same thing. 0.181 is your actual error, which is Pythagorean. You take the square of your easting error, square of your northing error, take the sum of that, 0.181, that's your actual error, your linear precision. You're out 0.181, and your relative precision is, again, they do this a little bit backwards, but you divide the distance traversed, which they should have done 311.35. They just rounded that to the foot. Looks like they're just trying to get to the nearest foot. They're rounding a little bit more than what I would say is common in the current era. But you divide 3919.35 by your computed error, and you get 1 in 21,000 as your error of closure, when in actuality 3911.35 divided by 0.181 gives you an error of closure of 21,610. Now we're going to come over to the corrections. So what we do here is just we proportionately adjust the error north and east. Well, there's two ways. The way they're doing it here is, looks like you're getting almost the same per leg, but typically what you would do, I think they're actually doing this proportionally, is the amount of error that you would put in to the leg between A and B would be 1045.50 divided by 3911.39. Let's do that. 1045.5 divided by 3911.35. That's 0.2673 of the error, which the X error is 0.179. So we're adjusting 0.0478, or here they are to 3 decimal places after they just told us to go to 4, but that would round to 0.04. And then if you're just looking at adjusted latitudes and departures, then you've got 1007.38. That would amount in an adjustment of 0.046. If you're adjusting this to coordinates as you go, you would add 1045 and 1007, divide that by 3911, and then add that portion of the error, such that at the very end, your adjusted coordinate is going to move your full error, which eliminates it and takes it back to the correct ending coordinates. And so some of their format here is a little bit hard to follow how they're getting some of this, because 43, 476, 506 is not too bad off of 43, 476, 52. And this gets you adjusted coordinates for the points, which is what we're after right here. And we'll work another example in the lab instructions. I just wanted to cover the theory of what we're doing. Save where this is. It looks like it's 41 minutes in. Probably go back to like 35 minutes in if you want to watch this again or come back to this. It is in the book, table 10.6, and the information that goes along with it. Now, Traverse computation sheet. This is just a blank standard format of how things are typically done. Notice they've got northing first and then easting. This is pretty much common. Not sure where this came from because they do have meters, but it really doesn't matter. It's whatever unit that you're using. We'll use feet. But this is something that would be part of an old file from decades ago, where a survey, whether it's a control survey for an engineering project or a boundary survey, it would use this format. I've gone into old files from old surveyors and saw where these were sheets and sheets, pages and pages, the bigger they are. This is one way to do it. From station A, you'd list the, from station A, I don't know exactly why A is there, but you'd be filling in like A, the back bearing would be, your back azimuth, probably what you use instead of bearing. And then you're turning to C after backside B. You'd have, say a 35 might be your back bearing, and then you're turning in a 90. So your forward azimuth would be a 125. And then, whatever correction you'd come back and add to get your corrected bearing down here might be a 125, 0116. You'd also get your true horizontal distance. That's where you correct for slope or the sum of your braking chain increments. Then you create, coordinates of points B referred to points A and arithmetic sums. This is just another example of what I'm trying to say is, as long as you understand the data and it makes sense, there are countless ways of organizing it. Now, one of the things that I want us to do, we're going to keep them simple. This is a 5-sided traverse. We're going to do 4-sided traverses. But figure 10.4 shows us how to plot a traverse for a boundary survey, and I want us to do this, even though software is a whole lot better and more efficient. This really helps illuminate when you actually plot it off on some grid paper. So we'll take the coordinates of our adjusted traverse and plot them on grid paper. And here, this is exaggerated, but I guess they're saying that A to B is the unadjusted, and then P to Q, Q to D. I don't know why they're not showing error in these others. They should. Really all 5 sides, but then adjusted, you come back to A and B as the final dot. Now, I believe they skipped over computing final adjusted traverse lengths. We're basically going to be taking the latitudes and departures back. So we'll divide. We'll take the latitude and departure, the square of those. Once we get our adjusted coordinates, we'll take the square of those, take the square root of the sum. That's the inverse distance. That's all inversing is taking the difference north, the difference east, or difference y, difference x, and computing the angle and the distance between a pair of coordinates. This is the basis of surveying computations. This is the essence. The simplest form is when you have two pairs of coordinates, we'll compute the bearing and distance between the two pairs. That is inversing. So I would have thought they would have had some better examples in the book, but they don't. I will provide some examples and work through them in the lab instructions. But do read section 10.10 and 10.11, which are basically the same, doing the same thing, and become familiar with that process, as we'll also cover in the lab instructions. So also in section 10.12, coordinate computations and boundary surveys, I'm basically just going to go back to that previous illustration where they call it radial traversing, but we're going to observe other points from our traverse than just the next traverse point. You're not going to have just one foresight at each total station setup unless you're doing a large boundary through the woods where there's just nothing else to locate. So you'll not only be determining bearings and distances between your adjusted traverse, but also you'll be determining coordinates on your side shots, and then we'll be determining bearing and distances between some of those side shots. Because if we locate a property corner A from traverse point 1 and we traverse 5 traverse legs down, and then from point 5 we locate the other, the iron pipe or the concrete monument at the other end of that property line, and it's B, then we determine coordinates for A and B, and then we will inverse the bearing and distance between A and B, and that's the bearing and distance that goes on the plat. So that's part of what we're doing there. Section 10.13, they talk about open traverses, and I'll just say this. You don't really want an open traverse for very critical information, and you're probably not going to be running any traverse if the data is not really critical and necessary. Definitely want to balance your angles, take the utmost care, but every setup that you get away from your traverse with an open leg, you're just opening the door for more and more error that never gets accounted for. So you're introducing more and more error into the coordinates reported from your open leg. So the authors of the book seem to think that open traverses are fine, but even in route surveys, you're not just going to run an open, unadjusted traverse out there. They did decades ago, and sometimes we find where they had errors in their original route survey because you can tell that the bearings on the roads don't match in a place or two. So be careful. Don't worry about that section of the book very much there. That 10.13. This table 10.10, computing the closing line from an open traverse. Honestly, that concept does not really make practical sense to me. I know there's adequate math theory to support it, but don't worry about that. You'll not see it on an exam, and you'll very likely never encounter that in the real world. We'll come back in survey 2 and talk about state plane coordinate systems, but it's good to go ahead and read about them. 10.15 just talks about, yes, we use computers for computations. That's why we're keeping it very simple in this class. Four-sided traverses so that we can just see the theory and understand what it's doing, so that you understand what's happening when you mash the button on your computer or your tablet or your data collector, and not just know that somebody told you to mash that button. One thing that does bear some discussion, it's one of our last slides, is locating a blunder. So when you get a misclosure or error at the end, you'll usually know where it is and how to go look for it, because if it's this much error from A to A prime, then you've got a problem. And in this example, say you started at A, traversed to B, set up on B, traversed to C. The distance is the mistake here. It's actually should be out here. Okay, actually we measured to C prime. We introduced this error, and so then the coordinates of every one of these points, the latitudes and departures are the same except for the leg with the error, but A to A prime is the same as this mistake. So you might run it up and say, wow, we've got a bust. Dang, we're out 7 feet. That's not good. What did we do? And you might figure out, okay, well, the bearing of the error is really close to the bearing from B to C. And if your angles measure good, because your angles were measured, in here at B to D. So your angles were measured correctly. This is the only error in this example, is this error made from C to C prime. So, for example, if you just inverted or transposed the numbers, it's actually 178, and you recorded 187. There's a 9-foot bust, and I have done that years ago when this is how we actually collected survey data with the field book. I have transposed numbers and wound up with busts. So if your angles are good but you've got a bust, that tells you it's a distance blunder. Now over here you're probably going to figure out in this example B, you've got the same bust basically, A to A prime, you got this same bust. Probably your angles did not sum. You're probably winding up with a degree or two or more of angular mistake. And in this case, they're telling us that the error was made at D. Well, we can also know that because it's just kind of practical. Software does this automatically. You can kind of do this in your head, but if the angular error, or the bearing of your error, just say in this example, it's north 5 degrees east. And you don't have any legs that are 5 degrees east. But what you would do is say, okay, I want to turn 90 degrees off of that from my starting and ending points and C. Because if you think about it, I mean, this is how we found lots of angular mistakes over the years. This is like a door. And that's the illustration I've used with employees for decades is, when you set up on D, and you've got this angular error here at the end of your traverse, this is where it is. It's the same thing as this angular mistake right up here. This same angular mistake here is going to play out at your closing coordinates. As you started, so let me go to a different color. We started here at A, and we've traversed around. Yep, we've traversed around, but we made this mistake right here, and we should have measured the line out here to this line, but instead we've measured that angle bigger, and that's our angular mistake. So this angle here from D to E, where the angular area is, it's going to be pretty much the same as the angle turned or computed. You can compute the angles by computing the bearings from D to A and D to A prime. From your preliminary coordinates on D to your starting coordinates on A, and from D to your actual ending coordinates where the bust is discovered. And that error bearing is going to point directly to where the error was made, because you're shutting the door. Basically, you go back to D, you return the angle, you find, you go, oh, that was wrote down wrong, somebody moved the back side, whatever. You put the corrected angle in, and it closes this door. And then, instead of closing at A prime, you're going to close at A, and your error is going to be something more tolerable. That concludes Chapter 8 lecture. We will go into some coordinate calculations more in the lab instructions, and lab will cover a simple four-sided traverse and then how to adjust those coordinates. Until next time.